Hello everyone, myself Dr. Santyavi Kundu. I welcome you all to this lecture of soft computing techniques. This is the first lecture of module 10. So in this lecture, we'll try to understand the rough membership functions and dependency of attributes. First one is that rough set and membership functions. In classical set theory, either an element belongs to a set or it does not. The corresponding membership function is the characteristic function for the set. That is, the function takes values 1 and 0 respectively. In this case of rough set, the notion of membership is different. The rough membership function quantifies the degree of relative overlap between the set X and the equivalence class XB to which X belongs. It defines as follows. So here the mu x bx is equal to the cardinal number of the set xb intersection x by the cardinal number of xb, where xb is the set where x belongs to. X belongs to the equivalence class xb and x is the target set. So obviously this values lies belongs to 0 to 1. The value of membership functions mu x bx is a kind of conditional probability and can be interpreted as a degree of certainty to which x belongs to x, or 1 minus mu x bx as a degree of uncertainty. So rough membership function defines the degree of relationship between conditional and decision attributes of an information system. It is defined by mu rx, say mapping from set of all objects to 0 to 1, where x is subset of u, under the relation R, where u is the universe of discourse. It can be expressed in different form like coordinative form and probabilistic form, etc. In coordinative form, it is expressed as mu x rx is the cardinal number of the set xa or intersection x by the equivalence cardinal number of the equivalence class xr. Whereas in probabilistic form, it can be denoted as Pxx xr is the conditional probability of this equivalence class xr intersection x divided by probability of xr, where xr is the equivalence class of x with respect to r. This membership function is used to measure the value of uncertainty. So in this example, we will try to understand the rough membership functions. So let the U is the set of all objects, which is 0, 1, 2, 3, 4 set of objects. Indissociable relations with respect to some attributes is 0, 1, 2, 3, 4, 5. I mean 0, 1 to same value A, B the same value B, 3 and 4 have the same value B, 5 is the different value C. So target set X is equal to 0, 1, 2, 3, which is subset of the set U. So we need to find the rough membership functions of these things. So here you can write that the value of, where you can write that U is the equivalence class. So XU, define the equivalence class as XU. You can write in other notations. So here we calculate the value of rough membership function for each object. So first object is 0. So 0 is lies belongs to the equivalence class, which is 0, 1, 2. So here the definition is that x u intersection x target set x divided by equivalence class of u. So here u is equivalence class for 0 is 0, 1, 2. So the cardinal number of 0, 1, 2 intersection target set 0, 1, 2, 3 divided by the cardinal number of the equivalence class, that is 0, 1, 2. So intersection here is 0, 1, 2. So cardinal number of 0, 1, 2 is 3, here also 3, so it is 1. So the rough membership functions of 0 objects is 1. Similarly, the rough membership function of the 1 edge 1 also belongs to the equivalence class 0, 1, 2. So here the cardinal number of 0, 1, 2 intersection 0, 1, 2, 3. So that is also the set 0, 1, 2. Cardinal number is 3. Also cardinal number is 3. So 3 by 3 is 1. Similarly, 2 is also belongs to the equivalence class 0, 1, 2. So your intersection is 0, 1, 2. Cardinal number is 3. Here also 3. So it is also 1. Now 3 belongs to the equivalence class 3, 4. So the 3, 4 intersection 0, 1, 2, 3 is only 3. So cardinal number is 1. Here is the cardinal number of the equivalence class 3, 4 is 2. So it is 1 by 2. Similarly, the equivalence class of 4 is 3, 4. So the Rab membership function is the cardinal number of 3, 4 intersection 0, 1, 2, 3. So 3 is the number, so that is the 1. Cardinal, and cardinal number of 3, 4 is 2, so 1 by 2. So that another object is 5. So this equivalence class for 5 is 5. So here intersection is null set, cardinal number is 0, that is 1, so it is 0 by 1 is 0. So here is some diagram is that, so you know that is the target set, so this is the equivalence class, this is the set of all objects. In the case of lower approximations, you know that xa is a subset of x, so x equivalence class xa intersection x is xa. So here if x belongs to the lower approximations, then this value is always 1, as this xa intersection x, cardinal number of that, a cardinal number of xa, this is always xa, cardinal number of xa divided by cardinal number of xa, so that is 1. So the rough membership functions can use to define approximation and boundary region. So if the value of rough membership function is 1, then x belongs to the lower approximations. If it is greater than 0, then x belongs to the upper approximations. If this is 0 and 1, then x belongs to the boundary region. So there is some diagram. Suppose this is x, the element x, so that is the equivalence class Rx. So here target set is x. If nothing is common, then it is 0. If there is something common, then it is 0 and 1. If the relation entirely within the target set, then the value is 1, just like the lower approximations. So now try to understand the sum property. Let U, A, be an information system and X, Y is the subset of U. The rough membership functions mu X, A has the following properties. So here you can write that mu A X has the following properties. First one is that the value of mu x ax equal to 1 if and only if x belongs to the lower approximations. So we have x belongs to the lower approximations. For this case, x star, the equivalence class is completely subset of the target set. So xa intersection x is xa. So in this way, you will get the value is 1. So if x belongs to the outside of the upper approximations, then mu x a x is 0. So the value of Rab membership is 0. The value of Rab membership function is 0 because x belongs to the outside the upper approximation. Then there is nothing common. So here xa intersection x is null set. So the value is 0. If x belongs to the boundary region, then the Rab membership function is 0 to 1. So you know that is the lower approximation, the set is upper approximation. So this is the boundary region. So if x belongs to the boundary region of x, in this case, equivalence class x intersection x is not equal to the null set, and xa intersection u minus x is also not equal to the null set. So here mu x, the value of Rab membership function is greater than 0, here the value is less than 1, so it is 0 to 1. Now if indiscriminate relation of a x belongs to u, then mu xa is the characteristic function of x. So if indiscriminate relation x belongs to u, then the cardinal number of xa is 1 for any x belongs to x. Moreover, the intersection is also 1 if x belongs to x, and the intersection is 0 if x is not belongs to x, that is x belongs to u minus x. If x indiscriminate y, then mu xax equal to mu xay. So if x is indefinitely less than y, then these two are equal, hence we have these two is also equal. Now the next property is that if x is not belongs to x, I mean x belongs to u minus x, so the Rab membership function of u minus x is equal to 1 minus the value of Rab membership function, that is mu x a x for any x belongs to x. So here the definition of mu a u minus xx is equivalence class of x intersection u minus x divided by the cardinal number of that. So here you can write it, this is 1 minus, this belongs to xa intersection x cardinal number of that by cardinal number of xa, so that is the 1 minus mu x a x. Now another thing is that the Rab membership functions, the value of Rab membership functions of the two union of two sets x and y, x is greater than equal to the maximum of mu x a x, mu a y x for any x belongs to u. So here you know that cardinal number x union y is always less than the cardinal number of x. So here you can know one thing is that you can write the cardinal number of x union y is always greater than equal to the x. So here this mu x union yx is equal to the cardinal number of xa intersection x union ya, so that is greater than equal to xa intersection x by the cardinal number of xa. So you can write that mu x union y a x greater than equal to mu x a x. Similarly, mu a x union y x is greater than equal to mu y a x. That means that it should be greater than mu a x union y x is greater than equal to maximum of these two values. So that is property number 7. Now property number 8 is that, so here you know that x intersection y cardinal number of this is less than cardinal number of x. So here mu a x intersection y x is less than equal to minimum of mu x a x mu y a x. So here mu x intersection y a x is equal to the cardinal number of x a intersection x intersection y divided by cardinal number of xa, so that is less than equal to x cardinal number of xa intersection xa by cardinal number of xa. So you can write that the mu x intersection y x is less than equal to mu x a x. Similarly, mu x intersection y a x is less than equal to mu y a x. That means that mu x intersection y x is less than equal to the minimum of mu x a x mu a y x. So if R is the family of pairwise disjoint subset of U, then mu union of all R x is equal to summation of x belongs to R mu a x x for any x belongs to U. So mu union of R x equal to cardinal number of x union intersection union of all R union of all R sets divided by cardinal number of xa. So that is union of xa x where x belongs to R divided by cardinal number of xa. So that is summation of x belongs to R and mu x a x, where R is the family of pairwise disjoint subsets of U. Now the next concept is that dependency of attributes. So that is an important issue in data is discovering dependency between attributes. A set of attribute D depends totally on set of attribute C denoted as C imply D if all values of attribute from D are uniquely determined by values of attribute from C. In other words, D depends totally on C. If there exists a functional dependency between values of D and C. Formally, a functional dependency can be defined in the following way. Let D and C be subsets of A. We'll say that D depends on C in a degree k, where k lies belongs to 0 to 1, denoted as C imply D, K, it can be written as C imply K D. If K equal to gamma CD equal to the cardinal number of positive regions C with respect to D by total elements and cardinal number of U, where positive region of C with respect to D is the union of all x belongs to U by D, lower or union of all lower approximations is called the positive region of the partition U by D with respect to C, is the set of all elements U that can be uniquely classified to blocks of the partition U by D by means of C. Obviously, the gamma CD equal to the summation of x belongs to U by D, that is the cardinal number of lower approximations of x divided by U. So if k equal to 1, we say that D depends totally on C. If k less than 1, we say that D depends partially in degree of k on C. The coefficient k expresses the ratio of all elements of the universe, so which can be properly classified to blocks of the partition U by D employing attribute C and will be called a degree of dependency. So now try to understand one example. Suppose this is the decision table where C is the set of attributes and D is the decision table. So here U by C, so there is 8 object U1, U2, U3, U4, U5, 6, 7, 8, and the set of attributes are the same. So 1, 3 are same, so that is A, 2, 5 are same, so that is B, and remaining are different. So 4 is C, 6 is D, 7 is E, 8 is 8 is F. Listen, 1 to 6, 8 are the same, so that is Y, and 3, 5 same, so that is N, 4 is different, so that is V. So here that U by D, here x1 is this element, 1, 2, 6, 8, x2 is this element, 3, 5, 7, and x3 is 4. So we need to find the lower approximation of all these things. So first you find the lower approximations of all this. So here is Ax, x belongs to U by C. So x belongs to U by D. So you find all this, so that is lower approximation. So then take the union of all these. So now first find the lower approximation of Cx1. So here it is target set is 1, 2, 6, 8 C. So see which are properly subset. So properly subset is that 1 is this equivalent class will not be there as 3 is not present. This also not there, 5 is not present here. So only 6 and 8. So that is the lower approximation of x1. Similarly x2 is 3, 5, 7. So 3, 5, 7, this is not present, this is not present. So only 7 is present. Just fourth only 4 is present. So now the positive region CD is the union of all x U by D's, all lower approximations. So find the union of all these, so you will get 6, 8, 7, 4. So D depends on C in degree K. K belongs to 0 to 1, denoted as C imply D K, where K is equal to gamma CD equal to the cardinal number of positive region of C with respect to D by total number of objects. So again, positive region of D is union of X U by D, all lower approximation. The positive region of the partition U by D with respect to C. So here the positive region C D with equal to union of X belongs to U by D, or lower approximation, that is 6, 8, 7, 4. So here the cardinal number of this thing is 4, total number of object is 8. So the value of gamma equal to 4 by 8, that is 8 by 2. So you can write it K. So here C imply half D. So that is the partial. You can also write C imply D half. So that is the partial dependency. So I hope in this class you have understood the dependency attribute and also the rough membership functions. So take any previous problem and try to find the dependency attributes. In question 2, you try to find the rough membership functions from any previous questions. Find rough membership functions of any previous problem. And these are the references of today's class. Thank you.